I give you the Vietnamese name. Eigenvalues in Vietnamese is giá trị riêng. Eigenvector means vector riêng. So what is eigenvalue and what is eigenvector? Now suppose that we are given a square matrix A of size n by n. Then we have a question: do there exist a non-zero matrix of size n by 1 denoted by x, so that ax is a multiple time of x? That is, I write the question in the sentence, but now I will formulate it in the formula as follows. Suppose that we have A is a square matrix n by n. Suppose that we can find a number lambda. We call it a scalar. Suppose that we can find a non-zero column matrix X, the column matrix. And suppose that three things here, A, lambda, and X, satisfying the equation. Ax equal lambda x. Then, if we can find it, the number lambda will be called an eigenvalue of A. And the non-zero column matrix here will has name eigenvector of A corresponding to eigenvalue lambda. And I am going to explain to you why we need to have some words that corresponding to something here. Anyway, before that, I'm telling you the equation Ax equal lambda x has named fundamental equation for the eigenvalue problem. Okay, that is the name only. You need to remember that things only. Okay, now I give you some examples. A to be that very small matrix 2 by 2. Suppose that x1 to be the columns matrix here, and x2 to be the second column matrix, like that. Then if you multiply A by x like that, you multiply two matrices like that, you get 5, 5. And because of 5, 5 is a 5 times of 1, 1, means it equals 5 times of x1, because x1 is 1, 1. So it means that the number 5 here, is exactly the eigenvalue, and the x1, 1, 1 here is eigenvector of A corresponding to the eigenvalue 5. Now if we take A multiplied by x2, the second matrix, column matrix here, you get that thing. And that thing is exactly -1 multiplied by that column. And it's -1 multiplied by x2. So -1 is eigenvalue. And that column is eigenvector. And that, now you should pay attention. That eigenvector corresponding to the eigenvalue -1. That vector that is not eigenvector corresponding to number 5. It is corresponding to number -1 only. So now we have examples of eigenvalue and eigenvector. And the next one, you need to know how you can find the eigenvalue and eigenvector. That is a very generous exercise. Suppose that you are given a square matrix n by n. That is a matrix A. How you can find the eigenvalue, and then how you can find the eigenvectors. It is explained here by the fundamental equation of eigenvalue, means lambda will be eigenvalue of A if we have Ax equal lambda x, which x is a non-zero. If we can find a non-zero column matrix satisfying that Ax equal lambda x. So now we have an equation like that. And if you move lambda x from the right hand side to the left hand side, you get that one. Lambda I minus a x. I here is an identity matrix. So lambda I minus a x equals 0. And that one, because lambda I minus a is again an n by n matrix, so that one is a homogeneous system of linear equation. And by definition, an eigenvector must be 0. X must be a non-zero column vector, so column matrix. So X must be non-zero solution of a homogeneous system of equation, and that can have that homogeneous system of equation will have a non-zero solution if and only if the determinant of the coefficients matrix is 0. That I insist to you by the end of my review, the number 3 and number 4 there. So we need to have a determinant of lambda I minus a equals 0. So now we write it. Lambda is an eigenvalue of a if lambda satisfying that one. So if we compute determinant of lambda I minus a, it will be something like that. It is a polynomial in the degree n in lambda, and that equation has named characteristic equation of an n by n matrix A. So once again, that one is a polynomial in lambda of degree n, đa thức bậc n theo lambda. And we need to find lambda satisfying that, means we have to solve the system, to solve the equation. Chúng ta phải giải cái phương trình này để tìm nghiệm lambda. Nghiệm lambda đó chính là giá trị riêng. And the equation has named characteristic equation, phương trình đặc trưng of n by n matrix A. So that is the way we find the eigenvalue. And here, once again, we came back to the previous example. A to be that one. A to be that 2 by 2 matrix. And we need to find the eigenvalue of A. We write down the characteristic equation. It is a determinant of lambda I minus A. And lambda I minus A, you see, lambda I minus A will be lambda minus 1, minus 4, and minus 2, lambda minus 3. And if you compute determinant, you will get that one. And equation to be that, and obviously it has a solution lambda equal 5 and lambda equal minus 1. So we have two eigenvalue. The first eigenvalue is lambda 1 to be 5, and the second eigenvalue is lambda 2 equal minus 1. Next one. Next one, we need to find the eigenvector corresponding to each eigenvalue. For the first eigenvalue, we have lambda 1 equal 5. Then the eigenvalue corresponding to lambda 1 equal 5 means it must be the non-zero solution of that system of equation. It to be like that. And because the system, this homogeneous system of linear equation is very easy for you to solve it. So I write it here. The solution should be something like that. And we can write it like t time of 1, 1. And on that solution, will be solution of that one. And we want to have eigenvalue of A. And eigenvalue, I'm sorry, we need to find eigenvector of A. And eigenvector must be non-zero. So we require T is a non-zero. So anything here with T is non-zero will be eigenvector of A corresponding to phi. The next eigenvalue lambda 2 equal minus 1. Again, we consider the homogeneous system of linear equation like that. We need to find the solution x for that, and we require to have the non-zero solution, and the solution is here. And because x must be non-zero, so we require t is non-zero. So that is a procedure how to find eigenvalue and eigenvector. And the next example is just a little more complicated. I consider A to be the 3 by 3 matrix like that. First we find the eigenvalue. The determinant of lambda I minus A to be that, and we write down the characteristic equation. We get something like that. From here you get 3 eigenvalue. The first one is lambda 1 equal 1. The second one is lambda 2 equal minus 1. And the last one is lambda 3 equals 3. So we have 3 eigenvalue. And next, we need to find the eigenvector corresponding to each of those eigenvalue. The first one, lambda 1 equal 1. To find the eigenvector corresponding to that, we write down the homogeneous system of linear equation. Lambda 1i minus a to be that, and that is row equivalent to that one. Means we apply the Gaussian elimination to transform it into that thing. And please pay attention to that. The first column and second column containing the leading one. So the last column when corresponding to the free variable. It means that the solution will be as follows. The last variable, the x3, that is the last variable, is a free. We can give it any value t. And from here, you get x2 equals x3. So x2 equals t again. And from here, you get x1 equals minus 2t. Then the solution of that system of linear equation is t times of minus 2, 1, 1. But because we are looking for the eigenvector, and eigenvector must be non-zero, so we require t is non-zero. Next, for lambda 2 equal minus 1. Again, we write down the homogeneous system of linear equation. The coefficient matrix lambda 2 I minus a to be that one, and Gaussian elimination give us that matrix. And again, that one is a free columns. Means the last variable x3 again is a free variable, and the solution will be like that one. And then the eigenvector will be t times of 2 minus 1, 1. And again, we require t is non-zero because the eigenvector must be non-zero. The last one, lambda 3 equals 3. The last eigenvalue is equals 3. Then we write down the coefficient matrix lambda 3i minus a to be that. Gaussian elimination give us that matrices. Again, x3 will be free variable, and the solution will be that. And you get the eigenvector to be that one for any t, for any non-zero t is here. So that is the way we can find the eigenvalue and eigenvector. So for the eigenvector and eigenvalue, first we. So please switch off your microphone, please. Các bạn tắt microphone hộ cái ạ. Tắt mic hộ cái ạ.
Teacher, can I ask you a question?
Please.
In this case, it is T the eigenvector or all of the T and the matrix -2, -1, 1 the eigenvectors.
I said it already. Anything here is eigenvector except t equals 0. When t is 0, that will be 0, 0, 0. And 0, 0, 0 is impossible to be eigenvector because the eigenvector must be non-zero column matrix. Okay?
Okay, I got it. Okay, thank you.
So always we require that t is a non-zero. So let me continue. We stop about eigenvalue and eigenvector here, and we're coming back to that later. And now I explain to you some application of determinant. First, suppose that we are given a square matrix of A of size n by n. Then we have the so-called matrix of cofactor. So what is the cofactor? I recall for you. The cofactor Cij to be that one, where Mij is the minor corresponding to the Aij entry. I will not repeat some more like that, but however, Cij is. And then I take the transpose of that one, the text transpose of the Cij. I get that one. The cofactors matrix and take transpose, we get a new one here, and I call it adjoint matrix of A denoted by that one. That is the name only. First, I take the cofactor matrix and then I take transpose. I call it the adjoint. So why I need it? Need that here. Suppose that A is invertible matrix of size n by n. Then the inverse of A will be 1 over determinant of A multiplied by the adjoint matrix A. And you know already that A is invertible if and only if the determinant of A is non-zero. It means that we can always write 1 over determinant of A like that. But in order to find A inverse, you need to know the adjoint of A. So now we have it. Up to now we have it. Two different ways to find the inverse of a matrix. The first one, that is, you apply the Gauss-Jordan elimination to find A inverse. And the second way is now we have A inverse to be the 1 over determinant of A multiplied by the adjoint matrix of A. And of course, here you need to compute the adjoint matrix of A. And in some cases, it is very easy. Here is an example. Suppose that A is a 2 by 2 matrix like that, and I know that A is invertible, means its determinant is non-zero. Determinant of A to be that one, and I suppose that that is non-zero. Then you see adjoint of A to be that. Very easy to see. And then A inverse will be that one. It is here. So you see, for a 2 by 2 matrix, if you apply that one, it's very easy for you to see what is a inverse. Just a little bigger. If you are given A to be C by C matrix like that, the first example, the first exercise require you to find the adjoint of A and then use that to find A inverse. So how to do it? The first one, I repeat for you. It is here. That is the formula to find the cofactor. Now apply it. You get C11 to be that, and you need to do it 9 times to get anything. Now we have 9 entry for the cofactor matrix is here. Then adjoint matrix to be Z1, and the inverse should be like that. And because it is very easy to find the determinant of A, you get A inverse to be Z1, or you can write it in this form, and you can check A multiplied by that equals identity. So that is a way to find the cofactor, to find the inverse by using the cofactor. The next application of determinant is something about the Cramer's rule. Last week, I tell you already that the Cramer's rule saying that if we have a system of n equation and n variable like that one, and if you write it in the matrix format like that one, ax equal b, and Cramer rule saying that if determinant of A is non-zero, then the system must have unique solution. And now you can see, using the previous reason, previous slide, we can find the explicit solution for x1, x2, xn. We can give the exactly solution. In order to do that, I fix some notation. Suppose that A is denoted by Aij like that. That is a square matrix of psi n by n. Aij is a coefficient is here. Now I divide it into column. The first column I denoted by A1. Second columns I denoted by A2, and the last column denoted by AN. And X to be the column of variable, and B is the column of the right hand side here. Now here I denote Aj to be a new matrix of the same sign n by n. How we can have it? We replace the j's column of A by the column of right hand side. We delete the j's column of A and we replace the right hand side column inside that. Then we know that the solution for that, the system here will be the following: xj will be determinant of aj over determinant of A for any j from 1 to up to n. So we know exactly how we can find the solution. And in the slide I up on the model, there is a very careful, very detailed explanation for you. I will not explain here. You can read it by yourself. It is here, not so difficult. I give it for you. Just only require you to remember the formula how to use a cofactor expansion of a determinant along a column. And here I want to show you with some example. It is very useful to use that rule to solve a system of linear equation. Suppose that you are given a system linear equation like what you are seeing on the screen, and you need to find the solution. And now you can apply the previous slide. I mean, you can apply the Cramer's rule to find the solution. First, A to be that one. A to be that one. And I suppose that for you, it's very easy to find determinant of any 3 by 3 matrix. So that determinant to be 10. Now I take A1. A1 is obtained from A by replace the first column. The first column here will be replaced by the column of right hand side. So we get that one. And determinant of that equal 8. Now for the A2. A2 is obtained from A by replace the second columns by the right hand side column is here. And it has minus 15 determinant. And the last one, AC is obtained from A by replace the last column by the column of right hand side. And it has a determinant minus 16. Whenever you have anything here, so you get the first solution is X to be determinant of A1 over determinant of A. It is a 4 over 5. And Y to be that one, minus 3 over 2. And the last one, Z equal determinant of A3 over determinant of A. It is minus 8 over 5. So that is a way you can apply grammar rules to solve any system of linear equation. So that is the end of the lecture about the determinant. So I would like to tell you, if you look at the examples from the beginning of the class today, you see you have many skills you need to master in your hand. The first one, you need to master the skill to compute determinant of any square matrix, mainly with 3 by 3 and 4 by 4 matrices. The second one, you need to master the way to solve the system of linear equation, especially the way, especially the system of linear equation having infinitely many solutions. It is very important thing because you need to find eigenvector that I show you already. And in that, you need to decide which one is a free variable, which one is a leading variable or something like that. And of course, you need to remember, in order to do anything like that, you need to master the skill to use Gaussian elimination and Gauss-Jordan elimination. That is a very basic skill for you. Next, we continue with the lecture number 4. Lecture number 4 will concern with a new notion. It is somehow a little abstract to you. That is a notion of vector space. I will go right now. It is a very long lecture, so I will begin right now. In the high school, we study already the vector. The vector in high school, that is something of geometry. A vector in high school, usually you can imagine it is an oriented interval. An interval of straight line, and we give it an orientation, and A is origin point and B is ending point, something like that. Usually an intervals in the high school or in the real life used to represent some value like speed of a motion or forces or something else. And usually for vectors like that, you can define operation like addition, subtraction, and you can multiply it with a number. And here is some example, and I believe that all of you remember. Suppose that you are given a vector u, that is an oriented interval like that. You are given another vector v. How you can add them together? You need to put v to u, means the beginning of v will be at the ending point of u. Then the sum u plus v will be something like that. That is what we studied already in the high school. So now we begin with the new things. We are going to define what I call an n space, denoted by An. But however, my advice for you, that is, whenever you find something difficult to understand, difficult to remember, difficult to imagine, please take example. An example, usually you should take with very small number, n to be 1, n to be 2, n to be 3. That is what you study already in the high school. So let me begin our lecture now. We consider a sequence of n real number like that, x1, x2 up to xn. You put them together, and I call it an order n tuple. An order, I mean, you cannot exchange. If you exchange x1 here and x2 there, so you get another sequence. So that is two different sequence. An order means you cannot exchange. That is an order n tuple. And n space, I denoted a to the power n. That is a set of on order n tuple. That is a set of on sequence of n real number like that. Then now we call a system of n real number like that is a vector, and that is a vector of the n space An. It is a vector. I call it the vector. I don't know what it is, but however, I call it a vector. In case n equal 1, 2, 3, it is something similar to the vector you know already. But here, for any number n, I call it a vector. The example is here. For n equal 1, you have A1. That is one space. And if you look back here, in case n equal 1, in the sequence you have only one number x1. So because of that, in that case, A1 is exactly the set of on real number, and it looks like a straight line like that, and in Vietnamese usually you call it đường thẳng thực or trục số thực. Here we call it one space, nothing more. Now for n equal 2, that is, here we denote it by a to the power 2. We call it the 2 space. That is a set of on order pair of real number x1 and x2. And it is nothing but that is a coordinate, the coordinate plane, like that. In Vietnamese, you say mặt phẳng tọa độ. We can call it the two plane, a coordinate plane or something like that, but here I call it the two space. N equals 3. We call it denoted by A3 and call it 3 space. That is a set of on order triple of real number x1, x2, x3, like that. And that is a coordinate space we study already in the high school. Không gian tọa độ. The new one, with the example with the new one, that is the case n equal 4. That is new one. I believe that you have not yet studied that in the high school. That is 4 space. That space of on order quadruple of real numbers x1, x2, x3, x4, like that. Then I have some note for you. Usually, an n tuple x1, x2, xn can be viewed by two different ways. The first way, it can view as a point in the n space An. Please consider n to be 1, 2, or 3 to see. And down here, I am going to show you some example by the picture. So an n tuple x1, x2, xn can be viewed, can be considered by two different ways. The first way, you can consider it as a point in An. And in that case, x1, x2, xn will be considered as a coordinate. But another way, you can consider it to be a vector, and then x1, x2, xn will be considered as component, as its component. And the picture is here. In the case n equal 2, you see, that one is, we have a coordinate plane, mặt phẳng tọa độ. And x1, x2 can be considered as that point. It has two coordinates. X1 is horizontal coordinate, and x2 is vertical coordinate. But another way, you can consider x1, x2 to be the vector going from the origin to that point. It has two components. The first component is here. The second component is there. Again, I denoted by x1 and x2 as component. So we have two ways to consider a point, n tuple in n space. So I suppose that we should have a short break now, and then I come back.
All right, Professor.
Have you come back to the class?
Yes.
Okay, let's continue now. Now before the break, we study first about the n space with some example we know already from high school, like the picture you are seeing on the screen now. And next, we are going to define the operation on the vector. Once again, I repeat that any sequence like that, that is an element inside what I call the n space I. We call any sequence like that, we call a vector. And now we are going to define some operation on that. And first of all, suppose that you are given u and v, two vector in I. Then we consider u equal v. If and only if we have u1 equal v1, u2 equal v2, up to un equal vn, like that. One, okay. Then now we can define the sum of u and v. We call it the vector addition. That is addition of two vector u and v. That is a new vector or new sequence u plus v equal a new sequence. Sequence consists of u1 plus v1, u2 plus v2, un plus vn. And because it is a sequence of n real number, is again a vector inside I. Means you have u plus v is again a vector in I. Similarly, we can define a scalar multiplication. That is a scalar multiple of u by a number c or by a scalar c. Given a scalar c, we define c u to be a new vector with the component or with the coordinate cu1, cu2 up to cun. Then we have two operations defined here, and those operations has named the standard operation in Rn. That is the sum of two vectors and scalar multiple of a vector. We call it the standard operation in Rn. By standard means we have a non-standard operation. By the end of today, you are going to see it. Now, given a vector u, we can define what we call the negative of u. The negative of u denoted by the minus u, like that. That is a sequence with the coordinate minus u1, minus u2, up to minus un. So we have a sequence like that, and that minus u has a name negative of u. And then we can define the subtraction of two vectors u and v, or we call it the difference u minus v. That is a new vector with the coordinate u1 minus v1, u2 minus v2, up to un minus vn. And there is one special vector, very special vector, that is a vector consists of on zero. And I denote it by a fat zero here. That is a zero vector. It consists of 0, 0, 0 up to 0 here. Then now I give you the name. The zero vector, I mean the fat zero here, will be called the additive identity in Rn. And the negative here, the negative of u, will be called the additive inverse of v. I am going to return to that name later. Now I explain to you some property for vector addition and for scalar multiplication. Let u and v and w are any vector in Rn, and let c and d are any numbers. Then we have 10 property, but I list 5 property first. The first one saying u plus v is a vector inside I. The second saying u plus v equal v plus u, that is commutativity, tính giao hoán. The third one saying u plus v first and then plus w equals, we add v to w first and then add to u. That is associativity, tính chất kết hợp. And number 4 saying u plus 0 equal u, means if you add 0 vector to u, nothing change. And property number 5 saying if you take u plus negative of u, you get 0 vector. That the reason why we call it 0 is a additive unit, and here is a inverse, additive inverse of the vector u. Now I list next 5 property. Then those property concerning the scalar multiplication. The property number 6 saying cu is again a vector inside I. Then number 7 and number 8 are similar. That is distributivity. And number 9 saying if we multiply d by u first and then multiply by c, it equals if you multiply two number c and d first and then multiply by the vector u. And the property number 10 saying if you take the number 1 and multiply by the vector u, nothing change, you obtain again the vector u. So we have 10 property, and we are going to use that property in next few slides. Now here is some examples about the operation with vector in R4. I give you that, and you see it is very easy to work with those operations. Suppose that u, v, and w are given with the coordinate like that. That is a vector inside R4. And suppose that we have the equation like that one, x to be that, and c times x plus w to be that one. And your duty is to find x in each of those examples. The reason, the solution for the first one is as follows. Because x equal to u minus v plus cw. So we substitute u in here, v in here, and cw in here. You get that one. And everything very simple for you. So finally you get the reason x is here. And for the example number B is just a little more complicated because you have that one. So first you have to do the equation and to move x to be here. You get x equal u minus 1/2 of v minus c over 2 of w, and then you get that thing. So the computation is very simple, but however, it requires you some careness. I give you some more property of additive identity and additive inverse. Suppose that V is a vector in Rn and C is any number. Then we have the following property. The first one, the first property saying that the additive identity is unique. It means that if you have U plus V equal V, then U must be a zero vector. You cannot find any other vector than zero vector. So that when you add that to V, you get V again. That is the only one. The second property saying that the additive inverse of V is unique. It means that if you take V plus U, it is equal 0, then U must be minus V. U must be negative V. That is, you cannot find any other vector than negative V, so that when you add V, you get 0 vector. So that is it. And you have one more thing. If you take the number 0 multiplied by any vector V, you always get the 0 vector. And if you take any C and multiply by 0 vector, always get the 0 vector. And the last one, if you have CV, C multiplied by V is 0 vector, then you have only one of the following possibility. You will have C is 0 number or V must be the 0 vector. You don't have any other possibility. And the last, number 5 is not the last property. The 6 is the last property. That is, if you take negative twice, then you get V again. Negative of negative is V again, nothing new. Then, now I give you one notion. That notion will go from now to the end of the course of our course of linear algebra. That is the notion of linear combination. In Vietnamese, is a tổ hợp tuyến tính. So it says as follows: a vector x will be called a linear combination of the vector v1, v2, vn if x can be written in the form x equals c1 times v1 plus c2 times v2 plus up to cn times of vn. And here c1, c2 up to cn are numbers, scalar. And here is an example. Suppose that we are given x with the coordinate like that, and we know that u equals that, v to be that one, and w to be that one. For those vectors are in R3. And it requires you to show that x, the vector x here, is a linear combination of three vectors u, v, and w. How we can do it? It means that we need to find three numbers a, b, and c, satisfying that x equals a times of u plus b times of v plus c times of w. Now we substitute x in we substitute U into here, V into here, and W into Z. You get a system of linear equation like that. Minus B plus C X equal minus 1 is here. A plus B plus C equal minus 2 is. And the last equation is 4A plus 2B plus 2C equals minus 2 is here. And such a system of linear equation is, I believe that it is very easy for you to solve it. You get the solution A equal 1, B equal minus 2, and C equal minus 1. It means that X equal U minus C V minus W. Or you can say X is a linear combination of U, V, and W. That is a notion about linear combination. Now you should be we will coming back to the linear combination later, but now I want to compare something about the operation with the vector and the operation with the matrix. A vector in Rn usually is a sequence of real number like that, but anyway we can view it as a row matrix, like that. We can write it something like a row matrix like that. Also we can write it as a column matrix by this one. So we have 3 different ways to write vector. And we observe that the matrix operation we studied 2 weeks ago, that is the matrix addition and scalar multiplication of matrix, give the same reason if we apply the standard operation on the vector we have just defined before the break. We have just defined just 10 minutes ago. So now I write it down. For the vector, suppose that U and V to be that vector. Then if we apply the vector addition, you get that one, U plus V to be the new sequence like that. If you apply the scalar multiplication C by U, you get a new sequence or new vector like that. Now if we write it in the row matrix form, then the addition will give us the following: U plus V will be the addition of 2 row matrices like that, and we get new matrix like that one. The same like here. And also for the scalar multiplication, we have the same things. C U will be that. So it is quite similar to here. And the same with the column matrix addition and column matrix multiplication with a set, with a scalar C like that one. So we have, we can apply operation, standard operation on vector, or you can apply the matrix addition and the scalar multiplication of matrices for row matrices or for column matrices. It gives you the same reason. Now I continue by the definition of a vector space. Once again, I recall you that we list already 10 properties for standard operation on vector. Now we are going to use those 10 properties to define what we call a vector space. Now vector space, that is something very abstract. Abstract is a trừu tượng. That is not a geometric object. Now the definition is here. Suppose that V is a set. On that set, we have 2 operations defined already. Those operations has name addition and scalar multiplication. And suppose that those operations satisfying the axioms or the property I am going to list down here. if those V will be called a vector space, and any elements of V then will be called a vector. Okay, so now what is it? Axiom? What is the property? It is exactly the same 10 property as before. First, 5 property for addition, because here we have the first operation, I call it the addition. So we call it, we require U plus V means addition of U and V must be in V, must be another element inside V. Property number 2, that is a commutativity. U plus V equal V plus U. Number 3, that is associativity, tính kết hợp. Number 4, saying that inside the set V, we can have a very special element denoted by the fact 0 like that, so that for any other U in V, we have U plus fact 0 equal U. In that case, that element will be called a zero vector. And the last number, the last property concerning addition, saying that for any vector U in V, there is another vector also in V denoted by minus U, satisfying that U plus minus U equal zero vector. The zero is here. So we have first 5 property. So next 5 property concerning the other operation called scalar multiplication here. Number 6 saying that the scalar multiplication of any vector U and any scalar C is again an element inside V. Number 7 and number 8, that is about distributivity property. Number 9, that is here, we write it here. And number 10, if you take the number 1 multiplied by U, you get U again. So if you take a look here, you take a look on the 10 property in the definition of a vector space, it is exactly 10 property for standard operation on n space Rn. We list before the break already. I call your attention to the property number 1 and number 6. Why is that? Because it is very easy for students to forget it. So I call your attention to that one. And here is I summarize it. A vector space consists of 4 things. I call it 4 entities. I list it here. First, you need to have a set of elements. We call it a set of vectors. Then you need to have a set of scalar. And then you need to have 2 operations defined on the set of vectors. So that is 4 things. And here, the first one, the set of vectors usually denoted by V, that is a non-empty set. Then the set of scalar. Scalar, usually in our course, we call it a real number. But later, or maybe in the second semester or in next year, you can deal with some vector space with the set of scalar is a complex number. I don't know if you study it already in the high school, but however, I will omit it in this course. And then we need to have 2 operations. The first operation has a name addition. Usually it is denoted by the plus here. And the reason of the operation on 2 elements UV will be denoted by U plus V. We call it the sum of U and V. And the second operation has name scalar multiplication, usually denoted by a fat point like that. The fat point, the operation on C and U, denoted by C, U, like that one. So that is a notation for us. But however, I say that a vector space consists of 4 things. You should remember that. And the first example, V and two operations like that will be called a vector space. Sometimes when on the same set V, but you define another operation, it might be not a vector space. You are going to see today. And the smallest examples of vector space, that is, a vector space consists of only one element. Let's consider V consists of only one element. Then from the definition, the axioms number 4, there must be, that element must be zero vector, Then you see that on V you can have only one way to define operation, so nothing more. I leave it for you to imagine by yourself. The next example is exactly the n space. The n space with standard operation. The standard operation we defined already, and obviously that one is a vector space. Why is that? Because we use exactly the 10 property of standard operation on vector in n space to define the vector space. So nothing to verify here. Next, I call your attention to that one. Let V equal m by n. That is a set of on m by n matrices with a real entry. I claim that V is always a vector space. I can show you only in the special the easiest way. That is the case when m equal n equal 2. Then the vector addition is defined like that. The scalar multiplication is written like that, and it is very, very easy for you to verify that two operations like that satisfy on 10 property in the definition of vector space. So I want to stop here just a little to tell you from the very beginning of the lecture on the vector space. I explained to you in the high school, a vector usually you consider it to be a geometric object that is a oriented interval of straight line, something like that. But now with this example number 2 here, that is a space of matrices. Now a matrix will be a vector. It is no longer a geometric object. That is something very abstract, very abstract, and we call it a vector because it is an element inside what we call a vector space. But it is no longer a geometric object. And next slide will show you again another example. And here we consider V to be the set of all polynomial of degree less than or equivalent. Tập hợp tất cả các đa thức có bậc bé hơn hoặc bằng n. And I claim V is again a vector space. And in order to make it to be a vector space, we need to define two operations on that. And it is here. Suppose that we are given P and Q are two polynomials with that, then we define the addition to be that one, and scalar multiplication K of Px to be that one. And it is very easy for you to verify that two operations here satisfying on 10 property in the definition. And you can try the following homework. With that, with P and Q like that, what is zero vector. Zero vector must be a polynomial of degree less than or equal n. So which polynomial to be a zero vector here? Please answer me during the tutor class or something. The next example is again the function space. V will be the set of all continuous function defined on the entire real line. With the operation, we define it here, and I leave it for you to verify by yourself. So in both examples, number 3 and number 4 here, each element of the vector space is here is a polynomial and here is a continuous function, and it is no longer an objective and a geometric object. That is something else. But however, because it is an element inside a vector space, so it is a vector. It has a name, so vector. Now I explain you some property of scalar multiplication. Suppose that V is any element of a vector space V and C is any member. Then we have the following. If you take the number 0 and you multiply by any vector V, you always get the 0 vector. If you take any number C multiplied by the 0 vector, you get nothing but 0 vector. And if C multiplied by V equals 0 vector, then you will have C equals the number 0 or V must be the 0 vector. You don't have any other choice. And if you take minus 1 multiplied by V, you take the number minus 1 multiplied by V, you will get the negative V. So the next I will tell you, because I call your attention to the property number 1 and number 6. So now I tell you that to show something is not a vector space, you don't need to look at all 10 property in the definition of a vector space. You need only to show only one of the property is broken, is not satisfied. And here is some example. Let's consider V the set of all integer, and I claim that the example number 6 saying that V is not a vector space. So in Vietnamese, integer is a số nguyên. So V is a tập hợp của tất cả các số nguyên. It is not a vector space. Why that? You see, suppose that one is an integer, so it must be a vector inside V. And 1/2 is a real number. However, if you multiply 1/2 by 1, you get 1/2. 1/2 is no longer an integer. It means that it does not belong to the set V. You see, the first one, 1/2 is a scalar, is a number, the real number. But the one here is an integer. But when we multiply them together, you get 1/2. 1/2 is not yet is no longer integer. So you see, the property number 6 is broken. It means that the set of all integer is not a vector space. I say V, in that case, I say V is not closed under scalar multiplication. The next one is the following. I consider the set of all sequence degree polynomial. I say here, in Vietnamese, tập hợp của các đa thức có bậc đúng bằng 2. before I say polynomial of degree less than or equal n, but here I require the polynomial of degree exactly 2. Then I claim that one is not a vector space. Why that? Because if I take px to be x squared and qx to be minus x squared plus x plus 1, now you add them together, you get x plus 1. And x plus 1 now is a polynomial of degree 1 only. And it is no longer a polynomial of degree 2. That is the reason why that set is not a vector space. I say it is not closed under vector addition. I mean that formula saying the property number 1, the axiom number 1 in the definition of vector space is broken. So we have 2 examples. The first example saying property number 6 is broken. And the second example saying the property number 1 is broken. And because of that, those examples show some set which is not a vector space. Now I want to tell you something, some more thing. Because when we say about the vector in n space, that is in that case we define what we call standard operation. Now we define some more operation on that, which is not standard. I begin with a very easy case. Let's consider V to be R2. That is a set of on-order pair of real number, or something like you have a point on the plane. But on that, we define new operation. The first one we call the addition. The addition is exactly the standard U1, U2 plus V1, V2 equal U1 plus V1, U2 plus V2, like that. But now we define a new scalar multiplication. Suppose that we are given U1, U2, then its multiplication by a scalar C to be that one, C U1 and 0. That is a new operation. I call it scalar multiplication. And now we look at here. The examples require that we need to show that V is not a vector space. How to prove it? Here. You take number 1, you multiply by the vector 1, 1. By that definition, you get 1, 0. That's by definition. But however, 1, 0 does not equal 1, 1. It means that the property number 10 is broken. The property number 10 in the definition of the vector space is broken. So we see that V is not a vector space. It means the set V together with 2 operations we define here is not a vector space. So I think that we stop today here, and the next week we will continue about the subspace of the vector space. So you have any question to ask me?
No questions.
Okay,
No
so
questions.
Professor,
yes,
can you upload this slide to Moodle?
He
it's
already did.
It's already on the Moodle. I
Ah,
uploaded from yesterday.
okay.
Or this morning. I'm sorry. I uploaded this morning already.
Thank you, Professor.
Thank you, Professor.